Do you guys remember what an inverse function is? Do you guys remember what inverse functions are? So you might see a problem like this, where it says y equals 4x minus 3. Right? And we could plot a whole bunch of points. We could graph that line. We could do all kinds of stuff. You plug in a 0 and you get a, let's do this quick. Plug in a 0, you get a negative 3. You plug in a 1, you get a 1. Right? 4 times 1 is 4. 4 minus 3. Right? You plug in a 2 and you get a 5, and so on and so on. Right? Yes? Easy? So here's really what an inverse function is. Somebody give me a kitchen appliance. Stove. Spatula is not an appliance. Oh. Think simple. I want something easy. Microwave, dishwasher. Huh? Fridge. Toaster. All right, we'll use toaster. I like toaster. All right. So what an inverse function is, remember, a function is just a machine. Okay? So a function, think of it like a toaster, right? This is what a function is. All functions have inputs, right? We have a fancy name for that in math. We call that the domain. But that's just the inputs, right? For a toaster, what's the input? Bread, right? Did you just say toast? You don't put toast in a toaster. You put cold bread in a toaster. You put cold bagels. You put English muffins in a toaster. You put a Pop-Tart in the toaster, right? You don't re-toast bread. It just ends up burnt. Come on. Now, sometimes it's not dark enough. Yeah. And then you have outputs. In math, we have a fancy name for that. We call that range, right? So, we have a toaster. What's the input? Bread. What's the output? Nice, warm, hot toast. Yes? Sometimes burnt toast, right? Now, do all functions have limits sometimes, or most functions have limits? Yes, a toaster. You can't put anything in a toaster. Jell-O is a bad idea, right? You know, you don't want to put anything, forks, you keep that out of there. Like, that's a bad idea. You can't put anything in certain functions. You also can't get everything out of certain functions. I can't put something in there and get Jell-O to pop out of the toaster. Like, it's not going to happen. So, functions have inputs, outputs. If I make an inverse, right? An inverse function, all it's going to do is reverse the order. So, if I could create, and if someone could create this, this would be amazing. An inverse toaster. What would the input be? Nice, hot, warm toast. What would the output be? Cold bread. Now, what would be the benefit of ever having an inverse toaster? You can start over, right? Like if you burn your toast, you could put, let's screw this piece of bread up. This is the last piece of bread. I have left the stupid bread, right? We've all been there. We burned the last one. Now I could start over. I could put that burnt toast back in my inverse toaster, let it do its magic, and all of a sudden I got a cold piece of bread again. I can start over with the regular toaster. Wouldn't that be cool? So if y'all could invent that, that would be great. Shh. I'm not saying it's physically possible. I'm just saying it'd be sweet. Okay, so inverse functions, how do we make them? Well, the process is actually very simple. Step one, we are going to rewrite the function. But we're going to make some changes. Okay? We're going to rewrite it as is. But wherever you see an x, you're going to replace it with a y. And wherever you see a y, you're going to replace it with an x. What we're doing is we're switching the inputs and outputs, right? For the most part, our inputs are the x and our outputs are the y's, right? We're swapping those. We're basically saying, I'm going to rewrite that function, but any place I see a y, I'm going to write an x. And anywhere I see an x, write a y. And now, this looks a little funny because we like to solve things for y. So all we have to do is rearrange this and make it solve for y. So I would first add the 3, throw that to the other side, and then I would divide everything by 4. Oops. This function, this new function, is the inverse function to that. And what happens here is if I plot points, if I plug in a -3, what should I better get out? Before, I plugged in a 0 and I got a -3. Now I'm going to plug that -3 in, and what should I get out? A 0. Do I? -3 plus 3 is 0. 0 divided by anything is 0. When I plug in a 1, what should I get out? A 1. When I plug in a 5, I should get out a 2. Right? Simple? Yeah, you can sit there if you want. So that's what inverse functions are. This actually should not be new to you. How many of you guys actually remember somewhat dealing with inverse functions in the past? Yes? Now, graphically, something very interesting happens. If I take this function, so we got y equals 4x minus 3. That was our original. And now we got y equals x plus 3 over 4, right? Now, if I graph those on the same xy plane, this is a line, right? It's going to have a y-intercept of -3, go up 4 over 1. You're going to have this line that looks something like that. Agreed? Yes? Now, you graph that one, you're also going to have a line. I could rewrite this as y equals x over 4 plus 3 over 4. That is the same thing. So my y-intercept is 3/4. I'm going to go up 1 over 4. So it's going to look something like that. Now, the question, how is this becoming this? Now, let me show you another example here. Okay? I'm going to come back to that one and show you what just happened. I'm going to go even easier. Let's go y equals x squared. Parabola. Okay? Yes? Okay. What would the inverse function of that be? So if you switch the x and the y, x equals y squared, solve for y, what are you going to get? Squared x. Would you all agree this is the inverse function to that? Yes? Now, technically, anytime you take a square root, you have to remember to do plus and minus. That's important here because the positive square root graph looks like this. What's the negative square root graph going to look like? Now, what does it look like happened to go from that graph to this graph? It looks like it's a rotation, doesn't it? It's not. I can prove that to you. Plot one point. Plot one point. Give me a point that's on this graph. Plug in a number that you're going to square it. 1. Give me an easier number. 5. 3. Whatever. We'll go 2, so it's going to be on the graph. 2 squared is 4. So the point 2, 4 is on that graph, right? If this was a rotation, where should that point be on this graph? What quadrant? Quadrant 4, be down here, right? But if I plot that same point over here, the inverse point, the point 4, 2, it's over here. Get the idea? I kind of didn't draw my graph proportionally, but it works. Okay? Close. So, it's not going to be a rotation, right? What actually happens with every single inverse function graph is if you draw the line y equals x, has a y-intercept of 0, has a slope of 1, it goes to the point 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, right? If you draw that line and you reflect that image across that line, if I could take that line and spin it 180 degrees, this point is actually going to come down here. This point doesn't move very far and it goes right there. Does that make sense? That is actually happening. So this point way up here comes down here. That's actually what happens. Going back to this one, that's exactly what happened here. If I draw that line y equals x, this point is right there. This point is getting reflected across that line. This point moved up there. Does that make sense? That happens with every single inverse function. Okay? Technically, none of this should be new to you. Why am I bringing this up now? We are now dealing with problems like this. And that is in what form? What type of function is this? That is an exponential form. That's an exponential equation. We have to be able to deal with the inverse function to that. And this actually creates a problem, because if I rewrite this, if I want to say I'm going to find the inverse to that, what's step 1? So x equals 2 to the y, right? Solve for y. I got a problem now, don't I? How do I get that y out of the exponent? Like, that's a legit problem here. So, and something else happens interesting to graphically, because this graph looks like that, right? Goes to the point 0, 1. What's the inverse graph going to look like? If I draw this line, where is this point? Instead of getting closer and closer and closer to 0 here, we're going to get closer and closer to which axis? The y. It's going to, instead of going through the point 0, 1, it's going to go through the point 1, 0, right? And it's going to look like this. And then it's going to look like that. Make sense? This is where we need a new type of function. We call these logarithms. Now, one of the single biggest skills you need in this chapter is right here. This is where you're going to put a star in your notes. This function looks yucky. We're going to solve it for y just simply by bringing in a new type of function. We're just going to rewrite it because we can. Whatever the exponent is here, we're going to write that by itself on the left side. So this exponent goes here. We're going to write log. Whatever the base is here, the 2, we're going to put that as a little tiny 2. That's the base. Whatever it equaled before, that's the of. So the way you read this is you would say y equals log base 2 of x. That is how you would read that. Okay? What I want you to understand about logarithms. Logarithms are nothing but rearranged exponential equations. That's all they are. They're nothing other than rearranged log base. One of the biggest skills that we have to be able to do is take an equation like 3 to the second power is equal to 9. Would you all agree with that statement? If this is true, I can write that same statement in log form. That same statement would be log base 3 of 9 equals 2. These two statements are identical. These two statements say the same thing. We need logarithms because we're going to start dealing with problems where otherwise they're unsolvable. This skill of basically just going back and forth between these two forms, that's going to be the key to this whole chapter. We're going to get to some solving equations. And you're going to be able to manipulate some things. You're going to be able to do some things. You might get the ball rolling. And then there's going to be a point where you're going to get stuck. That equation might be in exponential form. If you're in exponential form and you're stuck, you're going to just switch it into log form. And the problem will become really easy. If you're messing with it in log form, what do you think you're going to do when you get stuck? Switch it into exponential. And all it is you're just moving the parts around and you're saying, this 2 goes here, this 9 goes in the of part, the 3 is your base. The bases are always the same kind of thing. Just get used to moving that around. What would 5 squared equals 25 be in log notation? Log base 5 of 25 is equal to 2. That's all that is saying. Those two things say the same thing. If I gave you something that said log base 4 of 16 is equal to 2. What is this back in exponential form? 4 squared is equal to 16. Make sense? And again, all we're doing is juggling here. We're just moving parts around. Okay? Once we start understanding how logs work, we can start actually manipulating a few logarithms. And we can start solving a few logarithms. Like, what would log base, we'll do this one, 10 of 1,000 be? Well, if I set that equal to x, what is it asking? Put that in exponential notation. It's saying 10 to what power is equal to 1,000? Well, this becomes exactly like that first time that make the bases the same. Isn't 1,000 just 10 to the third? So what's the answer? Make sense? If I said, what is log base 9 of 81 equals x? What am I asking you? What do you think, Laura? What do you think the answer is? 9 to the x equals 81. What's the answer? 2. 9 squared is equal to 81, right? That's all logarithms are. Please, please, please don't ever get scared of a logarithm. It looks ugly. It looks crazy nasty. But as long as you understand that all logarithms can be rewritten as exponential equations and vice versa, it's just going to be a tool that helps us solve equations with exponents. We're going to get to points where, like, we had problems that we've been dealing with logarithms already, or exponential already. Those I gave you some easy ones. But I could have made them a whole lot harder, and we didn't have a tool in our tool belt to deal with those. That's where logarithms are going to come into play. Okay? Everybody take a look at page 345. We'll do some more tomorrow. All right. I'll see you guys tomorrow.